Hi, and welcome back to Econometrics B in our second lecture on sample selection and regression models. So now we're looking at the case where we have incidental truncation, but where the selection equation is a appropriate equation, okay? So that's this one here. Okay, we're still interested in the same structural equation, so it's a linear regression model where where there's a linear relationship between y1 and x1, where x1 is exogenous in the sense that it's mean independent of u1. Okay, had we had no sample selection issues, we could just regress y1 and x1, and then we'll be able to estimate beta if we had a random sample. But we don't have a random sample. What we have is that we observe basically y1 only the case where the selection indicator s here is equal to 1. Okay, so here let's just dwell a little bit with this selection equation. Now we can assume that the selection is equal to 1 whenever x delta 2 plus v2 is positive. And since v2 here is normally distributed, it's going to be a appropriate selection equation so that the probability of selection is equal to the standard normal CDF evaluated x delta 2. Now it's the standard normal density because we normalize the variance of this v2 to 1, as we would do in any binary response model, since we could not identify the variance of this random variable anyway. Okay, that is really without loss of generality. So then what is explaining that binary selection indicator? Well, that's explained by two observable variables, x1 and x2. Okay, now these two variables are always observed also when we do not have a selection, so we can estimate this equation here. So x1, that's a variable that is entering into the equation of interest. Okay, so maybe your example, the leading example would be that where y would be the wage, observed wage, and then we'll try to explain that by education and experience and a bunch of other variables that we may think vary for the wage. Okay, that so these variables, well, they're likely to actually also explain the selection equation, which would be participation at the labor market, because you only observe y for people who are participating. So the same variables there, well, they have an effect on that selection. Okay, maybe people, they look at the potential wage offers, everything that explained what wage you could get in the labor market. Well, that would determine whether I'd like to participate in that game, right? So that's why we always have to exclude x1 in this reduced form for the selection. Okay, it's a reduced form because it could be that you had y1 somewhere in here, but that's completely substituted in, and then we have like a reduced form. And then there's some other variables, x2. These are variables that only explain selection and has no direct effect on wages, except for, of course, they have an effect on the observed wages in the selected sample through their effect on selection. Okay, so maybe there's some variables that explain why people select into the labor market, and then this may result in, for example, this group have higher wages, but it's not because the causal effect of x2 on y, but it's because the effect that comes through selection. Okay, so that's kind of the framework. So we can assume u1 and v2, they're both independent of x. Okay, so down here we assume that v2 is independent of these two explanatory variables. So we could estimate this equation here and get estimates of delta 2 on the sample that we have. Okay, and then also they're not going to have a direct effect. So that's what we need, right? And then again, we only observe y1 when we have a selection, but both x's, x1 and x2, they're also always observed. So for example, you would observe the education and experience and family background and stuff that explains both these selection and the outcome. Also for the people who are not working. Okay, so you also have those variables for the unemployed or self-employed or whatever is excluded from the sample. Okay, and so Then we assume further that these two, while they're independent of x, well, they're mutually mean dependent. Okay, so they are correlated. Okay, so you may see, and they're correlated in this particular way. So in this linear way. So the conditional mean of u1 given v2, that's linear index with a coefficient here. So if this coefficient here is 0, well, then they're mean independent. Okay, and we can assume they're mean and independent. So what does that mean that these two factors are allowed to be correlated? Okay, that means, for example, factors that is left out of this equation here. For example, well, I don't really have an example right now, but suppose we did not include education in trying to explain why people there are what their wages are. Then it's going to be in the error term. Okay. And of course, you're going to maybe have problems with exogeneity with respect to other variables, but let's just forget about that. So education is here, but then education is also determining selection. And so that's also in this error term. And then these two are just, they're going to be, it's going to be the same factors. Or, maybe, think of variables that are not potentially not observed, like ability. Okay, your ability or motivation, or things that drive, things that explain why you want to participate in the labor market, also explains why you get higher wages. Okay, for unobserved regions, and these things tend to be correlated. Okay, and so so we want to allow for that in this specified way. So this rules out, some forms of dependence this form for dependence rules runs out some joint distributions, but we're not making any particular functional forms assumption, but what this particular distribution is. Like, for example, we're not assuming that U1 and V2 are bivariate normal. Okay, does not rule out the bivariate normal distribution, but we're not assuming that they're bivariate normally distributed. And so, since we're not assuming that, making that assumption, well, then our identification strategy is basically robust to violations of these distributional assumptions, just as long as the conditional mean of U1 given V2 has this linear form. Okay, so that's basically less restrictive than just assuming that these two variables are bivariate normal. And actually, that's the assumption that we're going to make in the context of likelihood models that we'll cover later on. Okay. So to derive the regression model, the regression function conditional on selection, like we've done many times before, we'll first compute the regression function, not only on conditional on selection, but now also conditional on V2. Okay, so now we condition on not only X and selection, but also V2. Since we have already conditioned on X1, well, we can put X1 beta outside, and then we are left with this additional conditional expectation of U1 given X1 and V2. Okay, now because U1 and V2 are independent of X, we can actually reduce this this expression here to the following. Okay, so that means that we do not need to condition on X1, right? Because the U1 and V2 they were independent of X. Okay, so we don't have to make that conditioning, and then we're left with what we just made assumptions about before, how the relationship would be. This relationship between between U1 and V2 was this linear index here. So this is what we have. Of course, we cannot really use this regression function because we don't really observe what V2 was. But if we were, then we could regress basically y1 on X1 and V2, and then we'll be able to, then we have accounted for that selection. So the next part is to kind of integrate that out, okay, and take expectations with respect to that random variable that we do not observe. Okay, so we can get a regression function formulated in terms of observables, namely y1, x, and then the selection indicator. So doing so requires us to take expectations with respect to V2, and so we're going to take the expectation here conditional on X again, and the selection. Okay, so that's an additional term. This is just a constant that flips outside. And what are we left with? Well, we're left with the expectation of v2 conditional on X and then conditional on selection. But this is just a selection rule, right? So S is equal to 1 whenever v2 is greater than negative x2 delta, which is coming directly from this equation here. You just subtract that on the other side. Okay, so what does that mean? Well, what we have here is that this regression function for what we could work with, what we need to condition on in our sample is both X and the selection. Well, that depends on this last term here, and it turns out if that is not really necessarily non-zero. What it means here is that the unobserved part that explained the selection, well, that is basically that's basically, it has a non-zero mean in the selected sample, because these v2s, well, they are different for those that are selected than those that are not selected. So even though it has unconditional mean 0, well, for the selected sample, namely the case where this is supposed to be bigger than this value X delta, well, maybe they're actually bigger. And then if these two terms here are correlated in the sense of this in the specified way, well, then this coefficient here is going to be non-zero, and this is not going to drop out, and we have kind of a omitted regressor problem. So what we can do here is, fortunately, since we have shown enough about the distribution of these error terms, these v2s, we can derive what that conditional mean is and estimate it. Okay, and that takes the form of a truncated normal distribution, since this is basically a normal variable conditional that is bigger than some value. This is completely analogous to what when we talked about the sample or with sensor regression models, where we were deriving these conditional means in the objects of interest. There we also have basically a mean of a truncated normal distribution. Okay, and so that took the form of this inverse Mills ratio. So the next slide is basically not the next slide, but what a coming slide will derive that. Okay, now let's just focus on the simplest case first, where gamma is equal to 0. That is when u1 and v2 are uncorrelated. So, for example, take the example of ability, right? You may it's completely different abilities that determine whether you are participating in the labor market and whether you are getting higher wages. Probably not a very sensible assumption, but in that case, then selection would not be a problem, because the last term really drops out, and we can just do OLS. Okay, so let's move on to the more realistic case, where that is definitely not the case, where these two are correlated. So the same unobserved factors that explain whether you're participating are also the same factors that explaining whether you get higher wages. Okay, so in that case, this gamma 1 would be different from 0, and then you're left with this part here that we have to deal with. Okay, so OLS on the selected sample is going to be inconsistent due to the selection bias, because this is going to be this part here is going to be positive. Okay, it's a mean of a truncated normal. We're assuming basically that we are looking at a distribution where v has a 0 mean, but then we select only part of that distribution, namely those v2s that are bigger than some particular values. So that's going to be bigger than 0. Okay, and so that's a selection bias. You can also think of it as a variable that is correlated, that is an omitted variable. If you did just plain OLS of y1 and x1, then you have this additional variable that you're not controlling for. What does that depend on? Well, it depends on x, right? Because so it depends on x. What happens when we have variables that are omitted variables that are correlated with x? Well, then you get omitted variable bias. Okay, and so since now we want to move forward and try to see correct for this problem, we may actually want to derive that. And then since this v2 is standard normal distributed, and we know the selection rule, well, why don't we just try to calculate calculate a formula for this expression, which takes the form of a mean of a truncated normal distribution. And so we're going to make a little digression here, just to derive the expected value of a truncated normal. Saying, I think actually in a less rigorous way, been through this in the centered regression model. This is completely analogous to this, but here you have the expressions in the context of the current version of our structural model. So basically, I think I recommend, I think this is written up clearly, so I recommend you just pause it and look at the equations, and then you'll be able to actually do the math and come from these assumptions to this expression for the inverse Mills ratio. We're just really relying on V2 being standard normally distributed, so it has this density. The derivative of the density, well, that can be, you know, obtained by differentiating this guy here. Then you get this particular expression, and then really here, what is this? This is the mean of a truncated normal distribution. So basically, we take the mean of that truncated density, which has this, and again, to condition on, we divide by the probability that this selection is taking place. That is this probability, and then essentially we want to take the mean of V2, the conditional mean of V2, given that this holds. So how do you do that? Well, then you essentially integrate not over the entire support, but from the truncation point and upwards, right? Because that's where V is lying, right? So it's bigger than minus V delta. So that's why we're integrating from here and all the way up to here. Okay, and now then there's a little bit of, you know, reducing that, but really the main work from getting is writing up this, and then essentially the rest is just mechanics and, you know, manipulations with integrals. We are using the fact here that the normal distribution is a symmetric distribution, so that you get that the standard normal density evaluated x delta 2 is equal to the standard normal density at negative x delta 2, and then you also have you know, phi being equal to 1 minus phi at x delta minus x delta 2, right? So that's just the symmetry that's playing into these equations. You know, maybe it's a good exercise to sit down with pencil paper, so you can you get these steps, okay? And then the other thing here that I think I said that is you need to normalize the density for the probability for truncation. That's the probability of truncation that's entering down here, so that, you know, the truncated density is still integrating to 1 when you integrate from minus infinity to or from negative delta 2 to infinity. Okay, so that's really, so what are we getting out of all this? Okay, so if you're kind of zoning out now, what we got is really that this expectation here, this conditional mean of the truncated standard normal is essentially just equal to the PDF of the standard normal divided by the CDF of that, evaluated at x delta 2, and that is what we call the inverse Mills ratio of that expression. Okay, so then we collect the terms. Essentially, we just, you know, went back and then put an inverse Mills ratio right in here. Then we showed that was equal to this expression, and then we put it right back here in the place of that conditional mean. So that's what we have here. So now, basically, now you have your regression function of the selected sample that depends on things we potentially observe or can estimate. So if you were to know delta, we observe x, then we have a regression function that we can deal with. And by the way, this last term here, we also sometimes call that the inverse Mills ratio, and you know, for short, it's just a function lambda of x delta 2. It's not lambda times, but it's a function lambda of x delta 2, and that function lambda is equal to this expression up here. So that is another way to see here the sample selection as an omitted variable problem, right? So you clearly now you have an explanatory, you have your regression function being equal to x beta, but then plus this additional sample selection term that depends on S. This is a function of X, right? So if you were not including this in your regression, well, you're going to get omitted variable bias because this is going to be in the error term, and the error term would be correlated with X, okay? So probably not a good idea. So what Heckman suggests, and that's that's a Nobel Prize winner, so we, he tends to get good ideas, is why don't we just estimate delta, generate this regressor, the inverse Mills ratio, evaluated at the first step estimates of this parameter, include it as a regressor, and then we have it corrected for sample selection. And it turns out to work out beautifully. And that's what you're going to do actually in the exercise class. Work with this two-step estimation procedure that Hickman published in his econometrica paper, a seminal econometrica paper from 1979. That's really like a seminal contribution into econometrics, and so really actually worth a read. And so we're going to work with this particular procedure, what you have here on this slide in the computational exercises. So the procedure is the following: run appropriate on the selection indicator on xi. So that is both x1 and x2, okay, and then you estimate delta 2. From that, you generate the inverse Mills ratio, where the formula for the inverse Mills ratio, well, that's this one here. You just put in delta, and then you have that. You save that on your computer, so as an additional explanatory variable, then you include that in additional regression, and you just run OLS on y1 and x1 and then the generated regressor, and that's going to give you consistent estimates of beta 1 and also, of course, the coefficient to this variable. Okay, now if this coefficient is non-zero, well, then it actually and it's significant, then you have a sample selection issue, and you have corrected for it. So why don't we try to see if we can actually test that? We can test whether sample selection is an issue, so that we need to correct for it. Okay, so when gamma is equal to 0, there's no sample selection, but if it's non-zero, then you have a sample selection issue. Now, the problem is, and we didn't actually spend a lot of time on two-step estimators, but when you have when gamma is equal to different from 0, and you're doing following this two-step procedure, well, then asymptotic inference is actually complicated for two reasons. First of all, you're going to have heteroscedasticity, in the sense that the conditional variance of y1 given x and selection is different from the conditional variance of y conditional on x and not conditional on selection, and that variance here is not constant, so it depends actually on x. I'm not going to show this. I think it's going to take us too far, but I'm going to give an intuitive argument for an example in just a second. That's the first problem. That's a heteroscedasticity. Okay. Now, heteroscedasticity we can deal with. We can just calculate the robust standard errors that are taking that into account. So what about what about this fact that this is like a generated regressor problem? That's something we kind of warded over in our treatment of M estimators. We didn't really spend a lot of time on two-step M estimators, but it turns out in some cases the sampling error that you're getting on because you're estimating on a finite sample in the first step can have consequences for your ability to make inference in the second step. So I know that popularly you're not taking into account the fact when you're using the standard OLS standard errors that this is subject to subject to not uncertainty, but variance due to the fact that it's estimated on a finite sample, that there's some noise around. This is a stochastic variable, right? And so there's some circumstances about when you need to correct for it. So I'm not going to go so much into details about what those circumstances are, but we are in one of those circumstances, okay? And I recommend you to read the chapter in two-step estimators if you want to understand the difference. The bottom line here is that we really have non-standard inference. Okay, first because of the heteroscedasticity, and then because of the generated regressor problem that arises because of this two-step procedure. Okay, so the covariance matrix on this on the form that you find in chapter 12 with the robust variance covariance matrices, well, that's robust for heteroscedasticity, but it's not solving the generated regressor problem. Then you have to work with actually even more complicated variance covariance matrix. But then the question arises: can we still test for selectivity bias? Okay, can we still test the hypothesis that gamma is equal to 0? And well, we can, because under the null, we don't have a generated regressor. We don't have any heteroscedasticity. So the under the null, that is when there is no sample selection issue, when there is no generated regressor, and when this here these two are equal, and we know we have assumed homoscedasticity, well, then we have standard inference, and we can just use the standard formula as usual, t statistics based on the OLS standard errors. Okay, so that's important to have in mind. But if you want to, continue with the model, having accepted that or having failure to reject sample selection, well, then you need to correct your standard errors to make, say, confidence intervals of the beta coefficients and so on. Okay. And so here's the explanation. It's essentially what I said. You can do that test because under the null, gamma is equal to 0, and then you have everything is beautiful and there's no generated regressor. Okay, so how do we correct those standard errors? Well, there's essentially two ways, roughly two ways. Use asymptotic theory for M estimators. See that chapter. That's it's not that brain intensive, but it's brain intensive compared to computer intensive. Okay, and we're not going to do that because we didn't spend a lot of time talking about two-step M estimators. So then you can do the bootstrap, right? And that's what we just did with the sample selection problem, or the with the sensor regression model in the last set of videos. So I explained where you would resample from the original sample over and over again, get like lots of bootstrap samples, and then for each sample you estimate what beta is, and then you can draw the bootstrap distribution, say after 500 replications of the re-estimations of the sample. Well, then you can calculate the bootstrap distribution. Of course, when you do so, you have to estimate the entire two-step model, right? So you also have to estimate the sample selection equation. Okay, so you take your sample, a sample with replacement from your original sample. So you get both y1s and x1s and x2. You estimate the probit equation. You estimate the structural equation with the sample selection correction term, the inverse Mills ratio. That gives you beta. Okay, so then you've estimated your beta, and then you record that. Then you do the whole thing again for a new sample selection for a new selected sample from bootstrap sample, get a new beta, and then you get a new beta, and then eventually you get a distribution of betas. Okay, so the bootstrap is going to help you here. Okay. Alternatively, we can do a maximum likelihood approach, which is going to be partial maximum likelihood, just like in the case where we did the proof probit. We're not specified the full likelihood. And why can we do it in this case? Well, because we have not, we cannot really observe what is going on in the non-selected sample for the outcome of interest. So we're going to do partial maximum likelihood in this case. But even with partial maximum likelihood, we need to impose more strong assumptions. And for particular, it's not enough to just say that these two variables are mean independent or mean dependent with the conditional mean is equal to gamma 1 v2. You need to specify the joint distribution of these two random variables to do maximum likelihood. Anyway, we're going to look at it. Just a little comment on the heteroscedasticity due to the selection. Well, showing that these two are different would, I think take us too far, in the second year in the computational and economics program, computer science and economic program. So why would, but I can at least provide a little bit of intuition by the following example. So suppose that some values of X imply very low wages. So we're still in the wage equation with a participation selection equation. Okay, so some values of X are just implying low wages. Okay, and then these X's they would tend to imply a lower probability of working, right? You don't participate in the labor market if you get lower wages, right? That means more truncation, okay? And or more people are not selected, okay? And then that implies a lower variance of the error term in the sample of workers, in the sense these guys are more homogeneous now, and we don't have all these people who are not working, so they have basically a lower variance, and this means that the variance here clearly depend on X, the factors that explain why people would get those low wages. Okay, so that's why you once you select conditional, you derive the variance conditional on selection, you're going to get potentially lower variance in this particular example, and that variance, or you get a variance that depends on X, and that's heteroscedasticity. Okay, so I hope that made it clear, but that's the best we can do. Now let's move on. New topic, new model. Okay, so we're gonna do that now. That is the Topit selection model. Okay, and it's very similar to what we just had, in the sense that we're looking at the same structural equation, but now the selection rule is that you're selected into the sample if some other variable y2 is positive. Okay, the leading example here is y2 would be the hours of work, and then y1 would be the wage equation. Okay, and I'm not implying that all econometrics is about wage equations. Okay, it's just a good example to explain things. Okay, for example, in the exercise, you're not going to work with a wage equation for the Heckman sample selection model. You're going to work on auctions and firms submitting bids to procurement auctions for for road work. Okay, and there you got a selected sample, right? Because you only observe the bids for the people who are actually bidding on that auctions. We're going to talk about what the exclusive restriction potential might be. It could be something about what is the distance to that auction, and so on and so forth. Anyway, so that was kind of a little bit of a backdrop here, but there's so many interesting econometric models where there'll be selection problems. Okay, I'm just explaining it in the context of the wage equation. Anyway, so let's back to the example of the wage equation here, and then now y2, that would be the hours of work, and then the problem is you don't observe wages for people who work 0 hours. Okay, and so these will be selected. The sample will only be selected for the people that have positive hours, and then you may have actually then you in order to estimate the selection model, well, then you would estimate a Topit model for example, if this is normally distributed, well, for hours of work and a bunch of explanatory variables that explain how much people are working. Okay, so basically same distributional assumptions as for the Topit. It's just the specification here, or the functional form here, that's a little bit different. Okay, so again, X, that's both X1 and X2. So we have some variables X2 that does not affect the wage, but may affect how many hours of work you may have. So for example, I don't know, a classic example is the children at home, for females, hours of work, in principle should not affect the wages. But they probably do, so not the best example, but that's the issue with many exclusive restrictions. It's so always possible to criticize. Anyway, so just think of it right now. Theoretically, these are variables that's not affecting the outcome of interest. Again, U1 and the V2, they're independent of X, and we're going to assume that V2 here is normally distributed. And actually, no, this has a separate variance that we can identify because we're in the Topit model. Okay, so that's a typo. So that's not the assumption we're making. I think I'm doing a little bit of too much copy paste here. Anyway, so I'm not going to correct it now. I'll correct it later. Then again, these are mutually dependent with the same dependence structure. So you got the conditional mean of U given V2 is equal to gamma V2. Okay, so that's the thing. The key thing is now, instead of just observing 0 Y, whether this is positive, you observe the value of of this latent variable whenever it's above 0. So for example, just like hours of work. Okay, so like before, we have the sample selection, a two-step sample selection procedure, and again, we can derive basically the conditional mean of x conditional on selection as the following here. And now note here that this depends on gamma v2. So then we estimate again what we what we can do here is that we can estimate delta delta from the reduced form equation for for basically doing a topit of y2 on x, and then compute this residual here. Okay, using the observations of these residuals, and remember, these residuals, they are observed for the selected sample, right? Because of the positive, or because of the continuous part of the distribution where hours is not censored. Okay, so for that part of the distribution, there we can actually estimate the residuals, right? It's just, that's coming out of the topit model. Once you've estimated this delta, well, then you can also estimate these residuals, at least for the part of the distribution where y2 is not equal to 0. Okay, and that's actually the part of the distribution that we need, because we can because we're working when we're estimating the second step, we're only working with the selected sample. So if we had a estimate of this, well, then we could just do, oh, well, that's in the second step. So using observations only where y is positive, that is when you got the selection, you can estimate beta simply and this coefficient for on the selection term simply by a simple OLS regression. So that is the second step, y1 and x1, and then these generated residuals. So so that's another two-step procedure for doing estimation of sample selection models, regression models. A few remarks on the topit selection. We can do again, we can do the sample, the test for sample selection selectivity bias under the null that gamma is equal to 0. We can test that hypothesis. And again, just like I explained it before in the context of the probit selection model, we can use the standard t statistics and based on these OLS standard errors, because these are valid under the null of no selection. Again, we have a potential generated regressive problem, but that is only a problem under the null. So if you want to test the hypothesis that gamma is equal to null, well, then you need to derive the distribution of the test statistic under that distribution and under that hypothesis. And then under that hypothesis, well, then these are standard normally distributed, these test statistics using the standard OLS standard error. You can use this OLS standard errors. We can estimate the residuals V2 directly. We don't need to compute the inverse Mills ratio, which is kind of, inverse Mills ratio is really like a generalized residual, okay, that's coming out of this binary response model. So it's a little bit like that. What is this residual taking into account the selection? Exclusive restriction, that's important here. We don't really need to allow for any have any exclusive restriction. So we can have actually x1 equal to x, and that would cause no problem, since V2 always have separate variation due to the variation in V2, right? So here, that this variation is going to have separate variation from this explanatory variable here, even though the explanatory variable here is explaining is inside here and explaining y2, but this residual here is going to have separate variation from that variable because of that variation that you have in the left-hand side variable. So hours are varying, and so these two here are not perfectly correlated. If you go back a little bit further and talk about the sample selection probit model, well, here you have this coefficient, and in principle, if you have x1 here and did not have an exclusive restriction, right? So that x is equal to x1, well, then you have x1 here and you have x1 here. You have two, basically x1 is appearing twice in this equation. Well, in principle, you could still estimate the equation because this inverse Mills ratio is a nonlinear function. But where is that nonlinearity coming from? Well, it's coming from distributional assumptions about the error term, okay? So that specific functional form of this inverse Mills ratio hangs crucially on the assumptions of these of the errors being normally distributed. Okay, so that's probably not the best idea in this case. Okay, so but you don't have that problem for the Topit selection because you have the separate variation in the variable y2. Say, for example, the number of hours that is separate from that variation in this Planisware variable. So when you include v2 here as an oppressor, these residuals, well, they are depending on x, but they are also depending on y2. So you don't have perfect collinearity. So I think that's kind of a conclusion here, that this exclusion restriction is actually not required. Okay, whereas whereas that is the case for Probit. And actually, the vast majority of empirical studies is using Probit selection rather than Topit selection. So you need to know about exclusive restrictions, and that's the topic for the next video.